So in my last video we looked at this question which said prove that if the position function of a particle at a time t is given by this kind of two-term trigonometric expression, then the particle moves with simple harmonic motion. We've solved the first part. We've proved that it moves with simple harmonic motion. How did we do that? We took the first derivative to find the velocity, second derivative to find the acceleration, and we found that the acceleration could be written as a negative constant times x, the position function, and that's the definition of simple harmonic motion. The second thing I want to do is think about what is the amplitude of this thing. We found a way to find the period. Once I know what omega is, I can find the period. What about finding the amplitude for functions of this type? So what about finding the amplitude for functions of this type? Now remember what amplitude is. What does simple harmonic motion mean? Well, what we have are quantities called negative a and a, where a represents the amplitude, and have something here in the middle generally referred to as position 0. And with simple harmonic motion, what we have is some kind of object. We've got some kind of object that just moves back and forth between these extreme positions. Okay? And it moves back and forward in this way. It accelerates towards the middle, and then it reaches its maximum speed there, and then it decelerates towards the end, and then it stops at the extreme point, and then it accelerates towards the middle, and then it decelerates towards the end, and then it stops. So what we're finding here, we want to find the amplitude of this function. What we're trying to find is the amplitude, the value of a. So its position at this moment at the amplitude is called a. And we know some stuff about this. So I'm actually going to just delete a little portion of what we looked at in the last class. I'm going to think about what happens out here at the amplitude. So this is what I'm going to think about. I know the first derivative gives me velocity, the first derivative of the position function gives me the velocity function, and I'm going to think about what happens here. You know, what is the velocity out at this point? If we think about it, when the position is position A, what happens? Well, the particle stops at that point and then returns back down here and slows down, stops here, turns around, speeds up, slows down, stops. So the position is A when the velocity is 0. So one thing to note, to find the amplitude, that position will equal to A when the velocity is equal to 0. And that's going to be important. Now that's an important thing to understand, that the position is equal to A when the velocity is equal to 0. At that moment in time, things moving with simple harmonic motion, when they reach that amplitude point, their velocity will be 0. So what we have here is an expression for velocity. So what I'm going to do is set that expression equal to 0 and see what I can do with it. So I'm going to set the velocity expression equal to 0. So negative a omega sine omega t plus b omega cosine omega t. I'm going to set it equal to 0. And we know at the moment that this is equal to 0, that the position function is going to equal to a. So a will equal to all this at the moment when all this stuff equals 0. Solving there, I'm going to get b omega cosine omega t is equal to a omega sine omega t. Okay, and one thing I can do here is divide on both sides by omega. And maybe at the same time I might multiply on both sides by a. So I'm going to get AB cosine omega t. So I'm dividing on both sides by omega and multiplying on both sides by a. I'm going to get a squared sine omega t. Okay, so AB cosine omega t is going to equal to a squared sine omega t. And actually I want to just take this first term on the left hand side, and instead of AB I'm just going to rewrite that as b times a. In fact, b times a times all that stuff. So what I've done here, again, I've just set this equal to 0. I've kind of got one term on each side of my equation. I've divided by omega on both sides using my division property, multiply on both sides by a to come up with this thing. So one thing I can solve from here is that a cosine omega t is going to equal to a squared over b sine omega t. Okay? So that's important. So at the moment, when x is equal to a cosine omega t is equal to a squared over b sine omega t. And what I can do is take this value for a cosine omega t and substitute it in here for this value. Because when x is equal to a, so I'm going to take this value for x, I'm going to substitute it in here. When x is equal to whatever the value of the amplitude is, a cosine omega t is going to equal to whatever this expression is over here. So I'm going to take this expression for a cosine omega t and plug it into my original position equation while plugging in a for x. So therefore, when x equals a, we're going to get my original position function, which is x equals all this stuff. That's going to become a equals a cosine omega t. I'm going to write that as a squared over b sine omega t. Plus b sine omega t. A is equal to a squared over b times sine omega t plus b sine omega t. And what I can do is say, well, that means the amplitude is going to be, I'm going to factor out a sine omega t here from these two terms. And what I'll get is a squared over b plus b. And a squared over b plus b can be written as a single fraction as a squared plus b squared over b. So what I'm going to have here is a squared plus b squared over b. Okay, so that's my amplitude. Now again, still I have it in terms of sine omega t. So that's the first thing. I'm just going to keep that in my back pocket for the moment. That's my expression for my amplitude, and I'm just going to keep that in my back pocket for the moment. Just put it away and go back up here, and I'm going to think about this quantity, sine of omega t, at this moment in time when x equals a. So going right back to this equation, I know that b omega cosine omega t is equal to a omega sine omega t. So let me take that equation. B omega cosine omega t. B omega cosine omega t is equal to a omega sine omega t. Now what I want to do is think about a quantity for this. What could sine of omega t be at this moment in time? I'm going to think about this equation. I'm going to just divide on both sides by omega. I'm also going to divide on both sides by cosine of omega t, which will cancel that on the left. And sine over cosine, remember, is tan. And I'm going to divide on both sides by a. And to get this expression, what I'll get is b over a is equal to sine over cosine of an argument is equal to tan of that argument. So what I'm going to get is b over a is equal to tan of the argument. If we think the most obvious way to think about tan of an argument, which in this case is omega t, is the opposite over the adjacent. Using the theorem of Pythagoras, I can establish that that is a squared plus b squared. The hypotenuse is a squared plus b squared. So actually I can come up with an expression for sine of omega t based on this little relation for tan. Because tan is b over a, that means the hypotenuse would be a squared plus b squared, or if you prefer to say x, y, and or would be a square root of a squared plus b squared. So sine is opposite over hypotenuse. That's going to be b over the square root of a squared plus b squared. Okay, so sine of omega t is going to be equal to that. And I'm going to take that value for sine of omega t, and take that value there for sine of omega t, and I'm going to substitute it back in here into this equation which I found a moment ago. So the amplitude, we know when the velocity is 0 that the position is equal to the amplitude. And the amplitude, we said, can be written as a squared plus b squared over b times sine of omega t. And we've just found that sine of omega t can be written as b over the square root of a squared plus b squared. Solving here finally for a, well, b is going to cancel here, and we're getting a squared plus b squared divided by its square root. Well, any number divided by its square root, any number divided by its square root is its square root. That's the definition of a square root. So a squared plus b squared divided by its square root is just going to be the square root of a squared plus b squared. Okay. Now, that's a little bit involved. However, it's well worth just learning this kind of thing off by heart. These position functions have come up on Leaving Cert papers before. The proof that they're moving with simple harmonic motion is pretty straightforward. The proof that their amplitude is that is a little more complicated. So what I would do is I would just learn off. I would just try to remember, go through a couple of times, see if you can prove it, but I wouldn't try to prove it every time. I wouldn't try to find the amplitude by going through all those steps every time. I would just remember that a particle of this type will have a amplitude of the square root of a squared plus b squared. That's what I would do. Okay? A couple of other things to think about. What if you took the conjugate of that? What if you changed the sign? Would you be able to find an expression of the amplitude? I'll leave that up to you. But remember, you know, it's going to move with simple harmonic motion with an amplitude of the square root of a squared plus b squared. So, you know, what does that mean? You know, well, questions that come up all the time is, you know, find the amplitude of something like, let me make something up, 3 sine of 4t plus 4 cosine of 4t. So that's my position function. We can show that's moving with simple harmonic motion by taking first and second derivatives. Second derivative acceleration, show that's a constant multiple of this expression here. You will find that omega is going to be equal to 4. So the period of this would be 2 pi over 4, which would be pi over 2. And you will also find that the amplitude is going to be the square root of a squared plus b squared, which, as you probably know, is 5. So if you learned off by heart that position functions of this type will produce an amplitude of the square root of a squared plus b squared, that's well worth remembering. I'll look at one more example based on this in the next class. But go through the proof, make sure you can follow all those steps for finding the amplitude. But it can be proven that the amplitude is always equal to the square root of a squared plus b squared. So we can work problems like that. So if I was given this in the Leaving Cert, I would just hopefully have remembered this thing rather than going through all those steps. It is a little bit involved. I would just remember that functions of this type will produce an amplitude of root a squared plus b squared. Do think about, what if I change the sign? How would that change the amplitude? Okay,